I'm Melissa,
I'm Jam.
and I'm a chemist,
And I'm not.
and welcome to Chemistry for Your Life.
The podcast that helps you understand the chemistry of your everyday life.
So, Jam, today we're going to be talking about something that I have thought a lot in my life, and I have absolutely never done any work to investigate it, which is unlike me to some extent and sort of like me in another extent.
Okay. Interesting.
Okay, and
What an interesting lead in. I mean, I think you already gave me a hint about what this one's about.
yes.
But what an interesting way to build this idea.
The hint is, what is the wind? I guess I told you that it was wind for your file name.
Yeah.
But the question is, what is the wind? And also, what are cold fronts?
Okay.
And the thing is, I can't tell you how many times I've been standing outside and felt a delightful breeze and thought, that feels so good. What even is the wind? And I know it's like moving air, so
Yeah.
don't come at me with that. But why does the wind is probably like a better question. Not what is the wind, but why is the wind? Why does it exist?
Yeah. It's like we all know it's air that's moving, but where did it come from and why is it even moving?
Yeah.
Is as soon as you start to wonder down the rabbit hole a little bit, a few more questions, they are, for me and for probably most people that are not scientists or whatever, feel very unanswerable.
Unanswerable, right? And usually I wonder that when I'm outside doing not phone things. So it's not like I could just pull out my phone and look up what is the wind.
Right.
Or why is the wind,
Yeah.
So I've always thought about it. Like, as long as I remember standing on a soccer field as a kid and thinking, where does that come from?
Yeah.
But I don't ever remember doing anything about it.
Yeah.
But surprise, surprise, it's all about chemistry.
Nice. I am surprised by that. Wow. I can't believe it's chemistry for once.
For once. I was teaching intermolecular forces in my class yesterday, and I said, basically, they're the reason for everything. So that was funny.
And end of lecture.
End of lecture. That's it. Bye. Listen to Chemistry for Your Life. Just kidding.
That's so funny.
So not only are we going to talk about what the wind is or why the wind is, I think is, again, a better idea behind that, but also why is some strong and some's a gentle breeze? And also, what is a cold front? Because that kind of goes along with it.
Right.
So these are all kind of similar ideas.
Is there a word for like the opposite of a cold front?
I think it's like a warm front.
Okay.
I think.
That sounds right. I shouldn't know. I feel like
I actually looked at this in my textbook about weather, but I did the research for this like 2 weeks ago, which is uncharacteristically ahead of time for me. So I just looked at the diagram with the cold front, and it has this specific dome shape and then like the warm air, but I don't remember what they wrote on the warm air.
I feel like we're used to hearing about cold fronts more because it's warm here a lot.
Yeah.
But the idea of like warm air coming in is just normal. It's like that's what we already have normally.
Yeah. Well, also, I think you'll see maybe why we talk about cold fronts a little bit more.
Okay.
So let's talk about what wind is. It is air that is moving.
Mm-hmm.
But why does air move if it's just empty space?
Right.
Well, it's not just empty space.
Right.
So I actually made my students do this same thing.
Okay.
Visualize the air. So if you could shrink down to the molecular level or zoom in on the patch of air in front of you.
Okay.
What I imagine as a chemist is a lot of empty space that truly has nothing in it, and then a lot of very spread out gas molecules.
Right.
So this would be like carbon dioxide, oxygen, nitrogen. And when I visualize molecules in my mind, I kind of think of them, I do denote whether or not they're carbons, oxygens, or nitrogens with a letter. But that letter is usually bonded to another letter and surrounded by a cloud of electrons.
Right.
So there's something called an electron density heat map that shows where there's more electrons or less electrons present in a molecule. And I kind of picture something like that.
Okay.
So I imagine what the air looks like actually is empty space full of a lot of spread out molecules.
Okay.
So if you can imagine empty space with molecules in it, and they're vibrating, they're twisting, they're stretching out, they're shifting, and they're actually physically moving because they have energy in them.
Okay.
Okay. And they are not often interacting with the other molecules around them because molecules like to be spread out. And when they get to the gas phase, they have enough energy in them that they are able to be spread out.
Right.
And when they start to come close together to one another, that's when intermolecular forces come into play and they start to turn from gas to liquid. They start to connect with each other. There's less energy, et cetera, et cetera.
Right.
Okay. But gas molecules, they don't really like hang out in groups as much. I don't think of them as hanging out in groups.
Right.
I think of water as hanging out in groups.
Okay.
And I think of solids as jammed into as like jammed into a small space or crowded and really close together, and they can't move around a lot.
Right.
Okay. So that's what I visualize when I think about, or part of what I visualize, I guess, when I think about solids, liquids, and gases.
Okay.
So air is that gas. That's what I imagine. I made my students stare at the air today and think about what was in it. So all these particles are moving around. And if it's warmer, if these particles have more energy put into them in the form of heat and light, those particles move around more.
Right.
And then if it's cooler, those particles move around less.
Right. But not cool enough to where they become liquid, but still
Right.
gas, but just moving less than warmer gas would.
Yes. And we talked about something similar with water in the episode that my sister shared about some of her research and what sea level rise is.
Right. Right.
And I think we might be re-releasing that in a few weeks so you guys can hear about that again. Hear the expertise of the other Dr. Collini before she was Dr. Collini.
And that episode is like a deep cut in a way that is kind of crazy because it's such a good episode, but it was very early in the podcast.
Yeah.
And it was our first guest, I think, right?
Right.
Yeah. And so that was super cool. So many people have not heard that episode. And so we're going to...
It's one of my favorites of all time.
Yeah, it's so good. We're going to help you guys hear it by moving it back up in the feed.
Right. And something I appreciate about the work that Renee does is she, I talked about in one of the recent bonus episodes about science communicators that I really admire. And I talked about how I like people who are scientists to share about the thing, or people who are not scientists to uplift the voice of the scientist who's doing the work. And Renee does that, where she is trained as a scientist. She has a master's degree in ocean science. And now she communicates with people doing the research. And because she's such a good communicator, she can bring that to people making decisions.
Nice.
So her job is really science communication. So we talked about a lot of public figures that do science education to the public, but she also does science communication in another setting, really.
Right, right.
So she has a really cool job, and she'll talk about that all in that episode. And I really like that one.
Nice. Me too.
So we talk about a similar concept in that episode, which is why we went down that rabbit hole, that when molecules have more energy put in, they typically move more. Sometimes that means they also expand, right? They spread out and take up more space.
Right.
Okay, so what that means is warm air rises.
Okay.
And people talk about that a lot.
Yeah.
But people don't talk about why.
Right.
Warm air rises because the molecules are moving around more and they're spread out more. So these molecules in this specific part of the air, there's maybe less of them in the same space as if it was a cold part. And so the warmer air is less dense.
Got it. Okay.
And that's why if you've ever heard warm air rises, that's why.
Okay.
It's literally less dense air. There's less air molecules in the same space, so it's more spread out, so it can rise more easily.
Got it.
It's just less heavy. Just like if you do something where you mix water and oil, the one that's less dense will just sit on top.
Yeah.
The warmer air will just move up and stay on top of the colder air.
So if you had like a cubic inch, basically, like that amount of space, and you're able to count the particles, the molecules of nitrogen, oxygen, whatever else is in there. In the warm air, it would be fewer. than the cold air
Right.
per like, if you could really like
Per
easily
cubic inch. Yeah.
measure the space like that.
Another
like
way
that.
I think of it is if there's a cube that can expand and contract, when it's cold, they've pushed out as far as they can and it's only a cubic inch. But as it gets warmer, the box can expand and now the same particles are taking up a larger space.
Got it.
So both of those are valid ways to think about it, but it's the same number of air particles just taking up a bigger space, making it less dense if you think about the box expanding.
Yeah.
And the other one, you're losing some of your air particles because they're leaving this space.
Or
gas
you know what?
molecules, I should say, not air particles.
Yeah. What's crazy too is exactly what we see with like, I think most people have probably experienced something like this where you have a balloon and if you take it from like one temperature to another, it changes the temperature of the gas inside, which causes the balloon to seem like it's shrinking or growing or whatever.
Right.
Like if you blow up a balloon inside and then take it outside into the winter cold. I think I've done this the other way around. I can't remember why I've experienced this exactly. Like, I don't remember the story, but like the balloon's size changes even though it's not like it has a leak or it's not like you added more air.
If you put a balloon at room temperature into a freezer,
right. There we go.
It gets like smaller and kind of crinkles in, and it would be more dense than this because it's contained in a smaller space than the corresponding earlier warmer thing. Yes. That is a really good connection. And also, I talk a lot about this time. I remember my lab teacher in college saying, if you heat a closed container, that's a bomb.
Yeah.
Because if you heat a closed container, those air particles, I just made up a whole new word. The air molecules, I don't know why I want to keep saying particles. The molecules in the air are moving and moving and moving, but they're in this closed container, so they're starting to try to expand and they can't. And eventually the pressure that they're exerting on the container will overwhelm the strength of the container and it will explode.
Right.
So that's why heating a closed container is a bomb.
Also, I think the particles thing is my fault because I said that once and then corrected myself to molecules. And I think I put the word in your brain.
Well,
it's not
and I'll say this. We're recording 2 episodes today. And I didn't sleep very much last night because I planned poorly for my life. I guess we'll just say that. And before that, it was very hot in my home because my air conditioner wasn't working. So I've had 3 nights of bad sleep and I don't have any medication for my lack of dopamine today. And all those things are combining for me to be misspeaking probably more often than normal. So if you guys will be graceful to me in this episode and the next episode, I'll appreciate it. I promise I know what I mean, even if that's not what I say. Okay, so all of that is how gases and those molecules act when you put more temperature into them, causing warm air to rise.
Right.
But if you can imagine these molecules you've been looking at in the air, warming up and rising, all of those molecules are going to be, say, if we're looking at Jam's front yard, those will be pretty evenly heated, all of the molecules above that.
Yeah.
And they'll start to rise up. And now there's nothing in the space where those molecules used to be. There's a lack of molecules.
Right.
And this brings in another chemical phenomenon. So the first one we talked about is sort of thermal expansion, is what it's sometimes referred to, that the idea that when things heat up and spread out. The other one we're going to talk about is diffusion. So those are your 2 chemistry lessons. You've had thermal expansion before. Thermal expansion explains why warm air rises. Diffusion we've also talked about before. Okay. We talked about it in the episode where we considered why thermoses keep coffee cold or insulated things or keep coffee hot. I was looking at your iced coffee.
Yeah.
So thermoses keep things insulated because they prevent diffusion. I don't know if I used the actual word diffusion in that episode, but we're using it now.
Okay.
So diffusion is the idea that if a molecule can spread out from someone else, it will.
Okay.
And human beings partake in diffusion, sort of. If you can imagine a bunch of people in a crowded lobby as soon as a door opens, they'll spread out and go into that other room as well.
Right.
Or if you have a party and everyone's in the kitchen because the living room's not set up yet, as soon as the living room's open, people will spread out. Some will still stay in the kitchen. Some will go into the living room.
Right.
So that is a good way to visualize a high pressure area with a lot of people. As soon as some of the pressure gets released with a door opening or whatever, the people can spread out and that relieves some of the pressure.
Right.
So if you have a pocket of air that's being heated up and there's air around it, so we'll just say all of DFW maybe is getting heated up evenly.
Yeah.
But there's a lake nearby DFW that's not going to take in temperature at the same rate.
Okay.
So our air gets heated up. That air is not getting heated up. So as our air heats up, it rises. It creates an absence of molecules beneath where it used to be, which is a low pressure area. There's no pressure because there's no molecules there. So the molecules adjacent that are in a cooler temperature see their opportunity and they will spread out. So warm air rises and cool air rushes in to the low pressure area to spread itself out, participating in diffusion.
Got it.
Diffusion. I said diffusion, but diffusion. Because low pressure areas, those don't really work for nature. We can't have really an absence of anything.
Yeah.
We don't like vacuums, right? So if there's an area where there's nothing, something goes into it to relieve the pressure on the other area, if that makes sense.
Yeah.
So when we feel wind, what we're actually feeling is cooler air rushing in to a low pressure area that was formed by warmer air rising and leaving.
Okay, I see.
And that's what wind is. It's the only two things. I mean, I'm sure there's more things, but the two main things that the gas molecules are doing are heating up, becoming less dense, rising. And then on the other side, the cooler ones that didn't receive that same heat are rushing in and getting some diffusion.
Yeah.
So the reason this happens is because the earth doesn't heat evenly. If the earth and the air above it heated evenly, there would be no air rising and other air to come in. Just air would rise and then cool down and sink and then rise and then cool down and sink, right?
Right.
Like an expanding ball almost.
Yeah.
An expanding, contracting ball. But because of something called specific heat and heat capacity, and because the sun hits the earth at different angles, there's all these factors that mean that certain areas get different amount of energy from the sun, and they take that energy in, and maybe it takes more or less energy to raise or lower temperatures depending on if it's water or land or concrete or whatever.
Right.
And we talked about that extensively in why are water and sand at the beach different temperatures.
Right. One of our earliest episodes, I think it was episode number 2.
I think it was episode number 2. And next week, we're going to re-release that so that you can think about what's going on there and how that unevenly heats the earth. And that creates these pockets of warm and cool air that then will diffuse and become less dense and rise and all the things to make wind.
Yeah. Okay. Wow. I didn't think about those relating so much. And also what's funny is that as you were kind of going through that explanation about the high pressure and low pressure areas of air, pockets of air, I remember sort of being given in some class as a kid, the explanation about weather stuff as just things always move from. There was kind of given a basic explanation without the like molecular level,
right,
understanding or whatever. It's like things always move into low pressure areas, or something like that. It was like, here's the rule, just know this for the future. And you'll always know this now.
But the reason they move into low pressure areas is so that they can relieve the relatively higher pressure.
Yeah. And I didn't understand that full picture. And, at the time, it might have been hard to explain it to me. But it makes so much more sense now.
Right.
And of course, you hear like low pressure areas or high pressure areas on the weather. Sometimes they say that.
Right.
That phrasing, the weather guy or whatever will say that. So I've heard that terminology a lot, but haven't understood it as well until all the explanation that you gave. So.
Well, and I tried to think of a way to visualize these molecules in a way we could wrap our mind around. So actually I thought about water in a bathtub.
Okay.
Now, our Earth is obviously much more complex than a bathtub, but let's start with water in a bathtub.
Okay.
And if you had water in a bathtub and you had like maybe a removable divider that was waterproof halfway in your bathtub,
Mm-hmm.
and you filled both sides up evenly with water,
Uh-huh.
if you remove that divider in the middle, nothing really will happen because both of those are experiencing the same number of molecules in the same space under the same pressure, temperature conditions.
Uh-huh.
But if you have something that takes all the water away, just like the cold air rises, if you could magically raise all that water up and make it less dense and make it float,
Uh-huh.
and then you removed the separator, then whoosh, water would rush over and make it evenly filled on both sides.
Right. Right.
So you've seen those molecules before in water rushing over,
Mm-hmm.
just like in a dam, just like if you can imagine in your bathtub. Water will try to get to where all the molecules in a contained space are experiencing the same environment.
Right.
Air does that same thing. It's just instead of humans forcing water on one side or the other, it heats up unevenly. One pocket will rise and essentially leave the area, vacate the space, and then cold air rushes in and
Right.
we feel the wind. So just like a waterfall, the wind is moving into a lower pressure area.
Right. Right.
Okay.
Interesting.
You can make wind also if you want, again, to see this phenomenon,
But not in the way you think.
but not in the way that Jam's thinking. That's such a dad joke. By filling up a balloon and then putting a hole in it, you can feel the high pressure air molecules in the balloon. As soon as there's a way out, they rush out and you can feel the movement of those molecules as a small breeze, right?
Yes. Yes.
So you can kind of make wind as an experiment at home in that way.
Yeah. That makes total sense. It's like it's all trapped in there. And as soon as you give it the ability to move out of its like higher pressure situation and it wants to.
Then it wants to.
Yeah.
And it will. So you've seen this in life over and over, but that's also what wind is, which is weird to think about wind that way, right?
Yeah. It's this massive scale.
Yeah, it's so many air molecules in so many different pockets and so many different systems that all come together. But it's a sort of simple phenomenon if it weren't so complicated.
Yeah. Yeah.
Like that sounds, you could just say wind is air moving from high pressure to low pressure. But then it's like, why? Why can we feel the wind? What's in the air? Why are there high pressure and low pressure? You know, there's so many questions that go into it, but then you could just boil it down.
Yeah. Yeah.
And I forgot to say that there are areas that consistently get warmer or cooler. And so there are patterns to wind. There's like certain areas that they know typically the wind moves this way at this time and then this way yeah.
Got it.
So that's kind of interesting too.
Yeah. So it's a little bit predictable in some ways.
It is a little bit predictable in some ways. And then more intense wind comes from higher pressure, lower pressure differentials. So it's rushing quickly to get there. Whereas light breezes, there's only maybe a small pressure differential.
Right. Right.
So that's why some winds are gusts and some winds are just gentle breezes.
Right.
And last but not least, what is a front? This is, I think, maybe going to be one of the hardest things to explain.
Okay.
I think people who have spent a lot of time with natural bodies of water will sort of be able to follow, but this is one of the weirdest things I think about fluid dynamics. And fluids are liquids and gases. So
Okay.
I'll try to use water to explain it. But
Okay.
have you ever been in the ocean or like been visiting the ocean and you can see where the water goes from like murky brown to clear? There's like a delineation.
I think I have. I'm not sure if I've seen it in person, but I feel like I know exactly what you're talking about, and I just don't know exactly where I've seen it. Maybe
Right.
in videos or photos or something.
So that's sort of two masses of water meeting each other. And it's weird because there's not technically a boundary,
Right.
but there's something that's keeping those masses together that's sort of acting differently.
Right.
A front is the same thing happening between air masses. So a
Okay.
front is a boundary between air masses. One warm air mass, typically, and one cool air mass. They're usually different both in temperature and moisture content, and moisture and temperature will also play into density as well.
Okay.
And also, moisture content can change how heat and energy are absorbed. So it's not just temperature, it's temperature and moisture and all the effects that come with that.
Okay.
So similar to a battlefront between armies, kind of, right? That's I read, but I couldn't verify that that's where this came from. There's a boundary between cold and warm air.
Uh-huh.
And when one air, I think of the cold air advancing, kind of like you said, but also because cold air advances when warm air rises.
Right.
Cold air advances in as the hot air is rising, and as that's rising, also clouds can be formed, going back to our episode from a few weeks ago.
Uh-huh.
And that can play into why there are weather events oftentimes like thunderstorms or dangerous storms right at the front.
Got it. Okay. Okay.
So the front is just a boundary between two air masses. But what's interesting, they showed what it looks like, and it's kind of sloping typically. Like the cold air is almost trying to wedge itself in under the hot air as it's rising.
Ah, okay.
So that's
okay.
kind of cool.
Yeah.
To visualize what a front looks like.
And when we experience the front, so most of us, experience them, we are staying in one place. The air is what's moving.
Right.
And we just have been in, a lot of times the way I think of it, we've been in the warm pocket. Like I remember a day in, I want to say like March, something like that, when a cold front came in.
Mm-hmm.
I was at the park, literally my wife and I had our son with us at the park. He was playing, and we were there when the air moved, and the warm air got pushed out of the way.
Yep. Or rose up and made space.
Yeah, made space.
Right.
And the cool air came in, and the temperature dropped so quickly.
Yep.
But that's how we experienced it, even though like those pockets are probably like, so massive.
Right.
And they have been doing this for a while.
Yes.
It just happened to finally happen where we were there, and we crossed over between them while the hot air moved away and the cooler moved in. But
and
it's always so eerie to experience it.
It is eerie. And sometimes you can see the slant. Like there was a picture in my textbook of the cartoon representation of what a front looks like. And then they showed a picture of rain slanting in like the exact same way. And I was like, is that rain slanting that way because the wind that's pushing in is like shaped like the cold front? Like
yeah,
that was wild.
Yeah,
so,
that is wild.
Yes, I thought that was very, very cool. And I don't think I really put together that a cold front was kind of just a block of wind almost.
Yeah, yeah.
Moving in a solid mass, and that played into air rising, water being in it, clouds forming, and that's why there are weather events.
And it probably wouldn't even be moving in if the warmer pocket of air wasn't getting warmer and continuing to rise. Like,
right. If both pockets of air were cold, that would be that.
Right. Yeah. If there was no change happening and constant, obviously there's always heat being put on the earth. There's always things happening that are changing stuff.
Always.
But if it wasn't happening, then this wouldn't be moving. But this hot air keeps moving and keeps rising.
Yeah.
And keeps being warm.
Yeah.
Or getting warmed again every day or whatever you want to say. And then that keeps moving, making space for... That's just so crazy.
And then it rises up to where it might be cooler, and then it starts to get dense again and can sink back down. And then, there's so many systems. And I think it is very complicated. And so I actually have reached out to a local meteorologist. I don't know if he'll actually be able to come, but he did respond to me, hoping he can come on and, as his expertise, share more. We know the chemistry behind it, but then he can just talk to us about what weather is and weather phenomena and what causes what. And I'm really excited, and I really hope that can come to fruition, because I really do want to learn about how weather is a result of chemistry. That's not something I really have even thought about until recently.
Right. And it makes sense that there's people who specialize in exactly that thing because it's complicated
Right.
enough. So for there to be somebody who specializes specifically in weather
Mm-hmm.
makes sense to me now.
There's a podcast called Ologies, and what I like about that is, if there's an ologist in that area, that usually means that there's so much about it, that there's an expert in it, and we don't know anything about it. Like, what? That's amazing. There's someone who studies completely lizards. It's so cool.
Yeah, that is crazy.
I think I've also been thinking about this because there was a lot of media attention around the Depp v. Heard trial.
Mm.
And it's very sad. I don't recommend you listen to it. But what I found really interesting are the experts who are basically finding totally different opinions.
Mm.
And I kept wondering, in chemistry, there is a lot of nuance. And I do talk about the nuance and what we don't know yet. And on really very difficult things or things that we haven't fully explored yet, there might be people who have theories that it's one way or the other.
Mm.
And so I understand that nuance very well, but this is in a new field. I'm getting to see the nuance in a new field. And I'm thinking both of these people are really well trained to have so many questions. And so I started to listen to a different expert who also is a psychologist who could talk about those experts and talk me through some of the gray areas in the same way I'm talking you through some of the gray areas.
Yeah.
And I realized I'm so interested in hearing really well trained people who also are very good at communicating their point talk to me about what they know. I love that.
Yeah.
I suddenly realized that that's one of my favorite things. That's why I loved Radiolab. That's why I like listening to Ologies. Like,
Yeah.
anyone who knows a lot about something and is good at explaining it to you is fun to listen to. So I've really been enjoying some of that. I'm not sure how I got on this topic, but that's been really fun for me lately.
Nice.
Oh, because we're talking about the meteorologist.
Yeah.
Yes. So I am really hoping we can have him come on, and then I'll get the joy of listening to someone else teach me about their expertise, because as much as I want to do that for other people, I also want people to do that to me.
Yeah.
I love learning. So I also wonder if maybe now that I'm not doing work all the time for my PhD, I have more mental space to learn other things, so that it's a new excitement again.
Yeah.
So yeah, that's kind of been I almost told you I guess I kind of told you my happy thing ahead of time.
Yeah.
All right. So normally you tell it back to me. I used a lot of analogies though. So if you just want to repeat my analogies, that's fine. Or if you have a better or a different analogy, you are welcome to use that.
So I don't feel sometimes when I need to do an analogy to explain back to you, it's also because I need to kind of check to see if I understand it.
Mm-hmm.
There's been a couple moments throughout this episode that I've been able to sort of do that on accident.
Right.
And ask a question and make sure I understand it. And so I think the gist of it that I'll check with you, but I think I get it pretty well, is basically it comes down to just the differences of gases having different density of the molecules depending on the temperature that a given pocket of gas has, basically. So a warmer pocket of gas, the molecules spread out more,
Mm-hmm.
and so it is lower in density.
Right.
When that happens. A pocket of gas that is cooler, for any number of reasons that happens, that pocket of gas, the molecules will be closer together,
Mm-hmm.
and it will be more dense
Right.
because of that. We have a great big world, and there's lots of different factors everywhere, all over this earth, that can cause air to be heated differently than
And
other air.
You've even experienced that when you walk into the shade.
Right. Even the shade, that's a good point.
Mm-hmm.
And so because of that, all this air in all different places is different temperatures, even slightly sometimes.
Mm-hmm.
And that means different density.
Mm-hmm.
And the less dense air, the hotter air, is always going to want to rise
Right.
because it is lower in density. And every time that happens in a small area on your front yard,
Mm-hmm.
I've got a tree in my front yard, but it doesn't shade the entire front yard. So
Right.
I've got a little bit of difference in air density there.
Mm-hmm.
But there's also these massive scales of differences of air temperature and air density that we can see because of different states that have different climates or different or bodies of water that are near large areas of land that are going to have different ways that they heat up and different amounts of.
Or even sand versus dirt. If you have something with a lot of soil and plants, and then you have a desert area where there's not as many or different types of plants and much more sand, which heats and cools differently than dirt or clay. Right.
And then every time that a pocket of air or a massive amount of air warms up and rises, there's always going to be that space it's leaving behind. And cooler air, even if it's just slightly cooler, is going to move in to take that place. It's just the way it works. There's not going to be just a part of our atmosphere that's completely devoid of air.
Right.
Like,
yes. Yeah.
it's going to take that place.
And what is that called?
And when that
Phenomenon.
That phenomenon is called diffusion.
Yep.
Nice. Okay. And we experience that as either a slight breeze or pretty serious wind.
Right.
And it also can be the reason tons of different weather things are formed because it also plays into the amount of moisture in the air, et cetera.
All that.
And that is wind.
That is wind. Good job. You seemed to really I don't know if I got it right. Just then you said that is wind ?
I was like, I was more like thinking, did I miss anything? But I do feel like you explained it really well. Like I don't. Sometimes we get to the explanation part where I have to say it back to you, and I'm like, oh gosh, wish me luck. We'll see how much really stuck. And other times I feel like, oh, I get it. It makes complete sense to me.
Well, I think this one, I spend a lot of time visualizing molecules. And I also try to get my students to spend a lot of time visualizing molecules because I think that's an important part of understanding chemistry. So I am then like, okay, well, what can I relate this to in everyday life to help you visualize molecules? So I have to use more analogies on ones like this where we're really visualizing a lot of molecules.
Yeah.
Or where the main idea is movement of molecules, because you have to have a model because you've never watched oxygen move, except you sort of have in a breeze in trees moving in it, but you personally can't zoom into the molecular level. So it's like, what can we use to equate what I think the molecular level looks like? Yeah. So I'm glad. Sorry for stealing your thunder and not letting you have an analogy, but that was a really fun one.
It's totally okay. It's okay with me.
Do you have any other fun things from your week that you want to share about?
Yes, I do. Thank you for asking. So
always, literally.
Last week, I got the chance to. I can't remember exactly when this is coming out, but it was Memorial Day, Monday, and a friend of mine who you also know, Jason, who was my co-host on my old podcast.
I thought you were going to make a joke that it was Mason.
Oh, no. I had done that before, though.
A friend of mine who you also know, your husband.
No.
Yes, Jason, he's been on the show before.
He's been on the show before, and you know him, and he was the co-host of my other podcast with me. But him and I and him and his wife and their son, who is about 3, came and hung out for like several hours, and we did a whole pool thing, and the boys got to swim and splash around and have fun. And it had been a while. Like Jason and I don't get to hang nearly as often as we'd like, and he doesn't even live super far away, but our schedules are just very in conflict with each other, and we both have a lot of our life dictated by having a kid, so we don't get to hang out very often. But he had that day off, and so we got to hang out for like 4 hours.
Oh, that's fun. And did your kids interact with each other, and was that cute? Yes,
they interacted. It was really cute. It was very fun. It was a perfect day for swimming. And so that was a blast, and all went very, very well, and we got to catch up a lot. So that was a huge highlight of my week last week. What about you?
That sounds really fun. Mine's going to probably seem lame in comparison, but...
That's always my goal. I mean, I just want my week to seem so much better than yours that you feel bad. I'm just kidding.
Well, I feel like I kind of already talked about it, which is that I talked about how much fun I'm having listening to that psychology expert.
Mm-hmm.
And I've just spent a lot of time thinking about how weird being an expert is.
Yeah.
And how important knowledge is, but also how much it has absolutely no bearing at all, your knowledge, unless you can present it in a compelling way.
Yeah.
And also how many nuances there are in fields with expertise.
Right.
And actually, he gave the example, if two chemists looked at the molecules that made up of a diamond, they would find that it was made up of the same thing. And that's true, obviously, to an extent, but initially there's probably disagreements about how the atoms within that moved and if there was even movement in atoms that are in a solid. There is this period of disagreement and not having a clear path forward in a gray area.
Yeah.
That is necessary, I think, to building foundational knowledge. And so I guess I've just been enjoying hearing about that in another field and hearing someone's take on how that plays out in the workplace, in real life and culture, because there's not a clear decision in an area. So that's been actually really fun. I've really enjoyed listening to that psychologist talk about the whole field of forensic psychology. It's been really interesting.
Nice.
So yeah, I guess I just have the brain space to learn. When I was in the throes of my writing, I only listened to podcasts that were like dumb chit chat podcasts. And I was not interested in learning. Radiolab or 99% Invisible would come up and I'd think, no, thank you. I do not want to think.
Yeah.
And now I'm getting excited to think again.
Nice.
That sounds so dumb, but that's kind of how that's played out. And I've really enjoyed it. I've just been thinking about it a lot. I think it's a cool idea. So it's a good thing to listen to while you're doing the dishes. It's fun to get into new podcasts. So yeah.
That is very fun. I love that feeling of a new audiobook or podcast, something that you just kind of can't wait to listen to more of later.
You're like, when can I do my chores so that I can listen to this?
Yeah.
So, yeah.
Well, very cool.
Awesome. Well, thanks for letting me go on and on about my expertise, Jam, and also letting me go on and on about how I love other experts going on and on about their expertise.
Yeah. Anytime. And thanks for sharing your expertise with us and for explaining the wind. Like, what the heck? One of the biggest questions of
man,
of the history of existence.
You try to make it seem a little bit like I figured out what the wind was, but I just told you
first,
what other people explained. Yeah.
So thanks for sharing that with us. And if you have out there, listener, if you have questions about the world, questions about your everyday life that you think may be chemistry related, please reach out to us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, FOR, Your Life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/Chem for Your Life, or tap the link in our show notes to donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode could be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to A. Kiwasong and A. Collini, who reviewed this episode.